this is your first time here, my name is Ali-Ayman and I'm an electrical and electronics engineering student. On this channel, I aim to make videos aimed at teaching STEM, so mainly maths, chemistry, physics, computer science and engineering, and other subjects like economics and finance, as well as study techniques and productivity. So this will be our fourth video on this series of videos named Atomic Structure. Make sure you watch the previous videos on this series if you haven't done so already. Today we'll be looking at mass spectrometry. We will begin by explaining all the main concepts and then answering some practice questions at the end. So let's make a start then. So the first thing we'll look at are the key objectives for today's video. So the aim is to understand what is meant by the relative atomic mass and molecular mass, explain how a mass spectrometer works, its stages and what it measures, answer time of flight mass spectrometry and mass spectra calculations, and analyze mass spectra. So we'll look at all these in detail in the next slides. So the first thing we'll look at here is what is the relative atomic mass exactly, or AR. AR is another way of saying relative atomic mass. Well, the relative atomic mass is the average mass of an element's natural isotopes relative to 1/12 of the mass of a carbon-12 atom. Right, so there are a number of key things we need to talk about here. So first of all, elements don't have atoms with just one mass number, right? So elements can have isotopes. So they can have atoms with the same proton number but different mass numbers or different numbers of neutrons, right? So we never really have an element with just one type of atom, right? And we need to account for those isotopes. So the way we account for those isotopes is we take the average mass of the element's natural isotopes, right? And we compare this now to 1/12 the mass of a carbon-12 atom. So 1/12 the mass of a carbon atom is used as a reference. The carbon atom is the only atom that has an exact mass of 12, and this is because neither the proton or the neutron, and these are the subatomic particles in the nucleus, have a mass of exactly 1. And then the relative molecular mass is the average mass of a molecule relative to 1/12 the mass of a carbon-12 atom. So the way we find the relative molecular mass is we find the relative atomic mass of all the atoms in a molecule, because ultimately a molecule is a group of atoms held together by covalent bonds. And again, these atoms in the molecule may also be isotopes. So we have to calculate the average mass of the molecule and then compare that, to 1/12 the mass of a carbon-12 atom, because the carbon-12 atom, as we mentioned here above, is used as the reference from which the mass of all other atoms is derived from. And here are the formulas for AR and MR, or relative atomic mass and relative molecular mass, down here. So what is the purpose of a mass spectrometer? Well, the mass spectrometer can be used to measure the relative atomic mass, AR, of the atoms in a sample. The mass spectrometer can also be used to measure the relative molecular mass of molecular compounds, right? So the sample can either contain, a substance that has atoms, or it can contain, a sample that contains molecules. It could be either. One real-life example of the use of mass spectrometers include forensic investigation, right, such as identifying illegal drugs. And there are many types of mass spectrometers, but they all depend on the initial process of ionization, as we will see. And the main mass spectrometer we'll focus on today is the time-of-flight mass spectrometer. And now the method of ionization used in a time-of-flight mass spectrometer will depend on whether the sample contains atoms or small molecules, or it contains large molecules, for reasons which we'll discuss. So how exactly does a mass spectrometer work? Well, first we need to talk about the conditions. So the apparatus for the mass spectrometer is kept in a high vacuum. And the reason why this is done is to prevent air molecules from absorbing positive ions or positive molecules. And if this were to happen, it would interfere with the flight times, because it would ultimately prevent the ions or slow down the ions when they're trying to reach the detector, as we'll soon see. The atoms or molecules in the sample can have different AR or MR values because of the presence of isotopes in the sample. And that's important because we'll see ions or molecules with different mass to charge ratios, and that's ultimately because of the presence of isotopes. So remember that isotopes are always present in the sample. The sample is vaporized in order to allow the atoms or molecules in the sample to become gaseous and therefore be able to travel freely through the flight tube and ultimately reach the detector, right? That's the ultimate goal. Right, so now let's look at the first stage that occurs in a mass spectrometer, and that's ionization. And the particular type of ionization we'll look at here is electron impact. And this particular method of ionization is usually only done for atoms or light molecules, for reasons which we'll discuss in a second. So ionization is the removal of an electron to form a positively charged ion, right? And an ion, if you don't remember, is an atom with an unequal number of protons and electrons. So it can either have more electrons than it does protons, or it can have more protons than it does electrons. And the reason why this happens is because electrons can either be lost or gained. This is to form ions, obviously, not to form molecules. To form molecules, electrons are shared, right? And the reason why atoms lose or gain electrons is because they seek to obtain a stable outer shell of electrons, and we'll discuss this in the bonding topic in the future, right? So if the sample contains single atoms or light molecules, electron impact is the preferred ionization method. The reason for this is because fragmentation is not really an issue, and what fragmentation is the breaking up of molecules into smaller molecules, right? And that's only really possible when we have large molecules. But when we have small molecules or single atoms, that's not really going to be an issue, right? So electron impact is perfectly suitable for ionization of atoms or light molecules. Electron impact involves firing high energy electrons from a hot metal filament. This hot metal filament has an electric current passing through it, right? And that's where the electrons come from ultimately. These high energy electrons are fired at the gaseous atoms or the light molecules in the sample, and then this causes one electron. There may be two electrons, and we'll talk about why that may happen, but usually just one electron will be knocked off all the gaseous atoms or small molecules from the sample, and this creates positively charged ions or positively charged molecules. Right, so here we have the equation, right, that represents what's going on in electron impact. So here, this X here, so this X represents an atom, right? So it can be of any element, so it can be of chlorine, fluorine, sodium, magnesium. It can be an atom of any element. And the reason I'm just making it an atom, for this equation, just to make things a bit more simple. But again, this can also be a molecule. It doesn't really need to just be an atom. The plus electron comes from the hot metal filament, and upon collision with the gaseous atom, an electron is knocked off the gaseous atom, leaving two electrons. So one from the atom and the other being the electron that was fired at the atom. Right, so this X here has lost an electron and turns into a X plus ion. And so we're left with two electrons in total, and those two electrons are right here. Right then, so another method of ionization we can use is called electrospray. So this method, is mainly used for large molecules or macromolecules. If the sample contains large molecules or macromolecules, electrospray is the preferred method of ionization, since fragmentation, i.e. the breaking up of molecules that can result from firing electrons in the case of electron impact, may be an issue, right? So if we were to use electron impact on large molecules, there's a good chance that these large molecules may break down into smaller molecules. They may do so a lot more when we use electron impact as compared to using electrospray. So it should be noted that electrospray is also suitable for use with a sample containing atoms or small molecules, since electrospray does not cause fragmentation and does not interfere with ionization and detection. And the reason why it doesn't cause fragmentation is because, small molecules or single atoms, it's really hard to cause them to break down into even smaller molecules due to the, smaller size. So fragmentation isn't really an issue to begin with for small molecules or single atoms. Electrospray starts with dissolving the vaporized sample containing either atoms or small or large molecules. Electrospray can be used with any of these, right, as we mentioned before. So they are dissolved in a volatile solvent, and the resulting solution is then forced through a hypodermic or hollow needle, which is connected to the positive terminal of a high voltage supply. And whichever type of particle is present will then gain a proton from the solvent, which ultimately comes from the positive terminal of the high voltage supply. And then this produces tiny positively charged droplets. And as the solvent begins to evaporate, the droplets become smaller until positively charged ions or positively charged molecules start to form. Figure 1 here shows the apparatus for electrospray. So you can see here the solvent evaporating, and then slowly but surely we're left with just the positively charged ions or molecules, depending on what is ionized. And then here we have another diagram which shows electron impact, so what we talked about in the previous slide. Oh yeah, one more thing, the red arrows on the mass spectrometer in each page indicates what it is I'm talking about, right? So it indicates which part of this mass spectrometer I'm referring to, right, as I'm talking about the particular stage or process. So the next stage is acceleration, right? So once the atoms or molecules in the sample are ionized, the next stage begins. The positively charged ions or charged molecules, again, this will happen whichever method of ionization was used, whether we used electrospray or electron impact. The positively charged ions or charged molecules are attracted to a nearby negatively charged plate due to the electrostatic forces of attraction. If you didn't know, like charges repel and unlike charges attract, and this causes the ions to move rapidly towards the negatively charged plate and even accelerate. So the next stage involves deflection and ion drift. Once the ions or molecules reach the negatively charged plate, they pass through a narrow gap in the plate, and this converts them into a narrow beam of ions. The ions then travel through the flight tube where they are deflected by a nearby electromagnet, which deflects the lightest ions most. So they pass through, this gap here, or this slit in the negatively charged plate, and they are converted into a beam of ions, and they pass through this portion of the mass spectrometer here, and this is called the flight tube. And here they're also deflected by a nearby electromagnet, right? And this deflects the lightest ions most. And the lighter ions accelerate, or more generally just move a lot faster than the heavier ions due to their lower mass. Here they accelerate, so in this stage when they're attracted to the negatively charged plate, they accelerate faster, and in the flight tube they also move faster than the heavier ions, and this again is due to their lower mass. The next stage is ion detection, and this is the final stage, I believe. So once the ions or charged molecules reach the detector, they all gain an electron and are discharged, and flight times are recorded. So an electric current flows when this happens, right? So when they gain an electron from the detector and are discharged, a current actually flows. And this creates a signal, and so this signal from the detector is sent to a connected computer. And the computer uses this signal to generate a mass spectra, and we'll look at exactly what that is in the next slide. And obviously, since we said that lighter ions or molecules, move and accelerate faster than heavier ions, lighter ions or molecules will arrive at the detector before the heavier ions. So now the question is, what is a mass spectra exactly? Well, the mass spectra is a graph generated by the computer after receiving electric signals from the mass spectrometer. So the ones we talked about in the previous slide, i.e. the signal made when the ions are discharged at the detector. So the mass spectra has the mass per charge ratio, MZ, on the x-axis, right? So right here, and the abundance of each isotope or MR on the y-axis. The mass spectra therefore shows the abundance of each atom in a sample that has a different relative atomic mass. And the mass spectra can do the same for molecules with a different MR in a sample. So it's important to remember that inside the sample we have atoms or molecules with different relative atomic masses and different relative molecular masses, and this again is due to the presence of isotopes. And basically the mass per charge ratio is the mass or the mass number of the particular atom or the MR of the molecule, and we divide that by the charge. So for the vast majority of the ions, the charge is going to be just 1+. So ultimately the mass per charge ratio will be the same as the mass number. So the different mass numbers for the isotopes on the mass spectra are taken into account in calculations for finding the relative atomic mass or relative molecular mass of the substance in the sample, as we will see. So low resolution mass spectrometry implies that the mass numbers of the atoms involved is either given to one decimal place or to the nearest whole number. What I'm basically saying is the MZ or the mass per charge ratio you see here, so 70 in this example, right? So 70-71. This is called low resolution mass spectrometry because these MZ ratios are given to either one decimal place or to the nearest whole number. So that's called low resolution mass spectrometry, but there's also high resolution mass spectrometry where the mass number is given to 5 or even 6 decimal places. So now let's look at slightly misleading mass spectra readings. So on the mass spectra, we may have a reading with a mass per charge ratio that is around half that of other readings, or just generally less than other readings. And this can happen for two main reasons. The first one is fragmentation, and this is particularly the case with large molecules or macromolecules. So this is where some of the molecules being ionized broke into smaller molecules or atoms. So we talked about this earlier, and just as we said before, especially if larger molecules are ionized using electron impact. So that's why we don't really use electron impact for larger molecules, but fragmentation may even happen with electrospray, albeit on a much smaller scale. The other reason we may have these readings is 2+ ionization, and this is where 2 electrons instead of 1 are knocked from the gaseous atoms or molecules, and this will cause the mass to charge ratio to be halved, right? So if the charge is 2+ instead of 1+, when we get the mass per charge ratio, and that's basically dividing the mass number by the charge on the ion. When we proceed to do that calculation, we'll have to divide the mass number by 2 instead of by 1, right? So that will cause the mass to charge ratio to be halved. And the lower the mass to charge ratio can be seen on a mass spectra if there is an MZ value which is almost half the rest of the other readings and has a very small abundance peak. And that's the key point here, very small abundance peak. These particular cases of fragmentation and 2+ ionization don't happen nearly as frequently as what is meant to happen, and that's just single ionization and ideally no fragmentation. So now it's time to answer some practice questions to put into practice what you've seen in this video. Right then, so here are the summary questions. I'd like you to read through these questions and answer them yourself first, and pause the video when doing this. And once you've completed, you can resume the video and compare your answers to the ones I'll display shortly. So the first question asks, explain why the ions formed in a mass spectrometer have a positive charge. So the reason for this is because electrons are removed from the gaseous atoms or the gaseous molecules during the process of ionization. So when electrospray or electron impact is done to gaseous atoms or gaseous molecules, an electron is knocked off from these atoms or molecules. And so when electrons are knocked off the atoms or molecules, the particular atoms or molecules will have more protons than they do electrons. So there's an unequal number of protons and electrons, and so ions with a positive charge will form. Now the second question asks, explain what causes the ions to accelerate through the mass spectrometer, and the answer to this is the negatively charged plate causes the ions to accelerate through the mass spectrometer, and that's because of the strong electrostatic forces of attraction between the positive ions and the negatively charged plate, since unlike charges attract. Okay, so that's the final answer. Now question 3 says, describe what forms the ions into a beam. Well, the answer to that is the gap or the slit in the negatively charged plates. So when the positively charged ions pass through this gap, that's what converts them into a narrow beam or into a beam of ions. So this is the answer to question 3. Now question 4 says, state which ions will arrive at the detector first. The answer to this is the lighter ions, right? Lighter ions move and accelerate faster than heavier ions, so they would be the ones that arrive at the detector first. I should have mentioned this before. So for question 5, figure 4 isn't here, so you can feel free to just pass over this. I can, maybe put a link for figure 4 in the description, and you can maybe attempt that later. Question 6 asks us to use figure 8 here. So it says, figure 8 shows the mass spectrum of copper, and it wants us to calculate the relative atomic mass of copper. So the way we would go about finding the relative atomic mass of copper is reading off the mass numbers first. And I say mass number because although here it says mass to charge ratio, the mass to charge ratio is the exact same as the mass number because the charge is 1. So the division by 1 just gives us whatever's here. So the isotopes of copper we have here include one with a mass number of 63 and one with a mass number of 65, and these have different abundances. So the one with the mass number of 63 has a relative abundance of around 70%, and then the one with the mass number of 65 has an abundance of around 30%. So now let's talk about how we would go about finding the relative atomic mass based on this mass spectra here. This is a really important calculation, especially for exam style questions. So the way we would find the AR, or the relative atomic mass of copper in this case, right, is we would multiply the mass numbers by their abundances in percentage, right? So we would do 63 times 70%, and then we would add this to 65 times 30%. And the answer to this is a relative atomic mass of 63.6. And that's the final answer. So those were just some basic practice questions. Now let's look at some more advanced mass spectrometry questions. So here's the first question involving mass spectra and finding the relative atomic mass. So please pause the video and feel free to answer these questions on your own. Once you're done, you can resume and compare your answers to mine. Right, okay, so the question says, a sample of titanium was ionized by electron impact in a time-of-flight mass spectrometer. Information from the mass spectrum about the isotopes of titanium in the sample is shown in the table. Right, so here we have the MZ, or the mass per charge ratios, and then here we have the abundances in percentages. So these are the same as the mass numbers of the different isotopes. So we have isotopes of titanium in the sample, right? So these are the different isotopes, and here are the abundances of those different isotopes. And the question wants us to calculate the relative atomic mass of titanium, right? So it wants us to take into account all these isotopes. Again, the way we do this is, just like before, it will be AR is equal to 46 times 9.1%, plus 47 times 7.8%, and then plus 48 times 74.6%. And then plus 49 times 8.5%. And so the answer to this to one decimal place is 47.8. And that's the relative atomic mass of titanium. Now for part B, the question says, write an equation including state symbols to show how an atom of titanium is ionized by electron impact and give the MZ value of the ion that would reach the detector first. All right, so for this question, we would have to write out a similar equation to the one we saw in the slides. So the one with the X, if you remember, the X gaseous atom, right? So we'd write something similar. First of all, the chemical symbol for titanium is Ti, and then Ti is a gas. In the context of the mass spectrometer, Ti is a gas because it's vaporized. And an electron is fired at this titanium atom, right? So you do plus 1e. And then this titanium here loses an electron, right? So this becomes a titanium 1 plus ion, which is also gaseous. And we're left with 2 electrons. So the one that came from the hot metal filament that was fired at the titanium, and the one that was knocked off from the titanium atom, right? And this is what we get in the end. The second part of the question says, give the MZ value of the ion that would reach the detector first. So the ion that would reach the detector first would be the lightest one here. So we just pick the smallest MZ value here, and that would be 46. So the titanium isotope with the mass number of 46 would reach the detector before all the other isotopes because it's the lightest one. Right, so here's the second question. Please read through it and just like before, try and answer this yourself. And once you're done, you can resume the video and compare your answer with mine. Alright then, so this question here says, a sample of sulfur consisting of 3 isotopes has a relative atomic mass of 32.16. The following table gives the relative abundance of 2 of these isotopes. Use the information to determine the relative abundance and hence the mass number of the third isotope, and it wants us to give our answer to the appropriate number of significant figures. Depending on your exam board, this may differ. You have to check with them obviously, but for the ones in the UK, that would mean either 2 or 3 significant figures. So we know that the relative atomic mass is 32.16, and the way we find the relative atomic mass is we multiply the relative abundance. So we multiply the mass number, right, or the MZ, or the mass per charge ratio, by the relative abundance, and we add them all up to get the relative atomic mass. That's how we calculate relative atomic mass. Multiply mass number and abundance, add them all together, that gives you your answer. So this is equal to 32 times 91%. And then we add this on to 33 times 1.8%. And now we have X, right? Because we don't know the mass number of the third isotope. So we just call it X. And we can multiply this by 100%. And then we can just subtract from 100% 91 and 1.8. And that gives us the remaining proportion of isotopes that don't include 32 or 33. So now we simplify this and solve for X like a normal linear equation. Alright, so now we subtract both sides by 29.714 and then continue solving for X. The number of significant figures I'll put this to is 3, right? So I'll write this to 3 significant figures, and the answer to 3 significant figures is 34.0. Right, obviously you have to make sure you write 3 significant figures. And that's the final answer here. So now we'll look at some time of flight questions, but there are certain things we need to clarify before talking about that. The first thing, what exactly is time of flight questions? Well, you'll recall that, after the ions, pass through that gap in the negatively charged plate, that they are converted into a beam of ions, right? And then they pass or they travel through a flight tube, and they're also deflected by an electromagnet during that time. So that period of travel through the flight tube is called the time of flight, or the time taken, right, to travel from the negatively charged plate to the detector is called the time of flight. And we can perform calculations for the light and heavy ions. So that was some context. Now let's look at exactly what are the details we need to know before looking at calculations involving this, which I'll do obviously. So lighter ions travel faster in the flight tube compared to heavier ions. Yeah, we talked about this before. The kinetic energy and velocity of the moving ions can be found using the following equations. And those are kinetic energy equals half mv squared, or half times mass times velocity squared. And the second equation is velocity equals displacement over time. And you may be expected to change the subjects of the above formulae and substitute them into each other in order to find certain values based on what is given. So you may be given velocity, displacement, and kinetic energy and mass, and you may need to find the time, in which case you would substitute this velocity into this. So let's say you had to find the kinetic energy and you were not given velocity. So what you could do is you could substitute displacement over time into velocity in this first equation here, and then calculate the kinetic energy, assuming you've been given mass, displacement, and time, right? So that's what we mean by substituting them into each other, rearranging them. You can obviously rearrange this formula here. You can multiply both sides by time, and this would become displacement equals velocity times time. Divide both sides by velocity and multiply both sides by time, and you'll get this equation in terms of time. Same applies here. You can rearrange this equation to get it in terms of velocity, right? Multiply both sides by 2, divide by mass, and then square root the other side of the equation. That gives you the equation in terms of velocity, and you can substitute that into here as well. So that's what we're talking about. Now the units are really important, right? You need to remember what the units are. So the mass is measured in kilograms, velocity in meters per second, kinetic energy in joules, time in seconds, and displacement in meters. And if you're not given the mass directly, you may need to find the mass, right, based on the mass number, right? So you may be given the mass number of a particular ion, and using this mass number, you will have to find the mass of the ion in grams, first in grams, obviously. So the way you find the mass of the ion initially in grams is you divide the mass number by the Avogadro constant. We'll talk about this more when we do the moles series, right? And this is equal to 6.022 times 10 to the power 23. So you divide the mass number, right, by this Avogadro's constant. That gives you the mass of the ion in grams. But then you have to divide this mass by 1,000 to get it in kilograms, which is what's needed when using this equation here. Kinetic energy equals half mv squared. Right, so you may not always be given the mass of an ion directly in grams or even in kilograms. You may just be given the mass number on its own and be expected to find the mass in grams and kilograms using that and the Avogadro constant. So now it's time to answer some time of flight mass spectrometry questions. Right then, so here are the time of flight questions. I'll go into them right now, right, because they're a bit complex, and in case there's a good chance you may not understand what to do, I might as well just do it now and show you what's going on, and then maybe later on I'll post another question in the description. You can attempt that on your own. So the question says here, chromium plus ion, right, travels along a flight tube of length 1.25 meters. The ion has a constant kinetic energy of 1.102 times 10 to the minus 13 joules. And this is the equation for kinetic energy, and it's the same one we saw in the slide. Mass is m is the mass of the ion, v is the speed of the ion in meters per second, and the mass in kilograms. The question wants us to calculate the time in seconds for the chromium ion to travel down the flight tube to reach the detector. And the Avogadro constant is this thing here, so 6.022 times 10 to the power 23. Don't worry what that exactly is right now. We'll talk about that in later videos. Right then, so in order to find the time in seconds for the chromium ion, we need to use this equation here. V equals S over T, where V is the velocity, S is the displacement, and then T is time in seconds. So we're looking for time, right? And the way we find time is we have to rearrange this equation here. But here we're not given V, so we're not given the velocity of the chromium ion. So we actually need to find V first, right? And the way we do this is we rearrange this equation for kinetic energy, right? So this is the equation for kinetic energy here. It's equal to mv squared over 2. So in order to get this equation in terms of V, we have to multiply both sides by 2. And that gives us 2ke equals mv squared. The next step is dividing both sides by m, right, to get this in terms of v squared. So we're left with v squared equals 2ke over m. Now to get this equation in terms of v, we need to square root both sides. And that leaves us with v equals the square root of 2 times kinetic energy all divided by the mass. So the problem here is we don't have the mass in kilograms. All we're given is the mass number of the chromium ion, which is 53, as you can see right there. So what we do now is we divide this 53 by the Avogadro constant L. I'm just going to write 53 divided by L, but on your calculator you need to do 53 divided by this number here, and that will give you the mass of the chromium ion in grams. So we'll have to divide that afterwards by 1000. That will give us the mass in kilograms, because that's what we need here to get velocity. It gives us 8.80, then there's more digits, times 10 to the minus 23 grams. Now to get this in kilograms, we obviously need to divide by 1000, and that gives us 8.80 times 10 to the minus 26 kilograms. So here's the mass, right? So we can make this equal to m. This is the mass we need for this equation. We're given the kinetic energy, which is 1.102. So now what we do is we substitute this kinetic energy and this mass into this equation here to find the velocity. So v equals the square root of 2 times 1.102 times 10 to the power negative 13, all divided by the mass, which is 8.0. When typing this in your calculator, I recommend use the answer button for the mass, so that you get the exact mass when performing this calculation. And so the velocity is equal to 1,582,480.022 meters per second. So now in order to find the time, we need to divide 1.25, the length of the tube, by the velocity. So the answer to this is 1.25 all divided by the velocity we have there. And this gives us an answer of 7.90 times 10 to the minus 7 seconds. And this is correct to 3 significant figures. So this is the final answer. Right, so now for another question involving time of flight. I'd like you to pause the video and attempt this yourself first. Once you're done, you can resume and then compare your answers with mine. Right then, so the question says a molecule Q is ionized by electron impact in a time of flight mass spectrometer. The Q plus ion has a kinetic energy of 2.09 times 10 to the minus 15 joules. This ion takes 1.23 times 10 to the minus 5 seconds to reach the detector. The length of the flight tube is 1.50 meters. And the question wants us to calculate the relative molecular mass of Q. Obviously use this equation and the other two equations we talked about. So in order to find the relative molecular mass, we first need the mass of the ion in grams, and before that in kilograms, obviously. So we need this equation, Ke equals half mv squared, and rearrange it for m. mv squared, multiply both sides by 2, just like before, equals mv squared. Now divide both sides by v squared. So m equals 2ke all divided by v squared. Right, so that's the mass. So in order to find the mass, we need the kinetic energy, which is given, but the velocity is not given, right? The velocity here is not given. So the first thing we need to do before we can find the mass is find the velocity. And in order to find the velocity, we need to use this equation here, v equals s over t. To find the velocity, we need to divide the displacement, or the length, by the time taken, right? So we have length and the time taken, so we do 1.50 divided by 1.23 times 10 to the minus 25 seconds. V equals 1.5 meters, all divided by 1.23 times 10 to the minus 5. And the answer to this is 121,951.2 meters per second. So now all we do is we substitute this into the equation to find the mass. So the answer is, So we do m equals 2 times the kinetic energy, and the kinetic energy is 2.09 times 10 to the minus 15. And divide everything by v squared. And so the answer to this is 2.81 times 10 to the minus 25 kilograms. The next step we have to do is convert this to grams. So we multiply this by 1000, and the answer to that is 2.81 times 10 to the minus 22 grams. So now we found the mass in grams. Now to find the relative molecular mass, we need to use this formula here. So we need to do x divided by L equals, I'll explain what's going on here. So x is the mass number, right? L is the Avogadro's constant. So you remember, if you want to find the mass in grams, right? So if you want to find the mass in grams, you need to divide the mass number by the Avogadro's constant. So now we're doing the opposite. We're trying to find the mass number. So to find the mass number, we have to multiply the mass in grams by the Avogadro's constant times 6.022 times 10 to the power 23. And the answer to this is 169 to 3 significant figures. And that's the final answer. One more thing I forgot to mention. This was not an ion, this was a molecule, but it becomes an ion after being ionized. Once we remove the electron, it becomes an ion, but just remember that this wasn't an atom, it was a molecule. So that's why we have such a large mass number here, right? So just keep that in mind. Alright then, so this brings us to the end of the video. I hope this was of great value. If you have any questions, please post them in the comments. I would be more than happy to help. You can also attempt more questions down in the video description. If you found these videos useful, don't forget to subscribe. And more videos are coming, so make sure you look out for them. Thank you for watching, and see you all next time. Goodbye.